Hey guys, welcome back to data analysis. We're working on exploratory data analysis. This is part 3 of the series on exploratory data analysis. Let's just hop right into it. Okay, where we left off, we were doing these density plots where we did the sepal data. Now let's try some violin plots. So, ggplot, we're going to use the iris data. Not minus, equals iris. Aesthetic, x equals species, y equals, oh, there should be a comma, y equals sepal length, color equals species, and geom violin, so that is our layer we're adding, theme, classic, and we're going to add where we want our legend. So we're going to say theme, legend, position equals, and we're not going to have, we're going to say none, no legend. All right, let's run it. All right, annotate. Let's look at violin plots for iris. So you can see here we kind of have our distribution of sepal length. So we've been doing sepal width, right? So we're looking at sepal length. We see that sepal length is shortest. We have kind of a normal distribution if you were to cut this in half. Shortest in Setosa, higher in vesicolor, highest yet in Virginia, or Virginica, excuse me. Now let's try the south data. All right, so if we do ggplot, data equals south cases, aesthetic, x equals state, y equals cases, color equals state, and we add geom violin as our layer, theme gray, theme, oops, and theme legend, theme legend position equals none. Alright, so we can see here our distribution. So you can see that the state that has the max number of cases, or the highest case, had university. Texas, definitely. Mississippi had no one that had that many cases. So if we were to rank what state had the university with the highest number of cases, it would be Texas, then Arkansas, then Louisiana, then Mississippi. Yeah, so it's just another way of looking at your data. Okay. Now let's take a look at residual plots. This is a graph that displays the residuals on the vertical axis and the independent variable on the horizontal. In the event that the points in a residual plot are dispersed in a random manner around the horizontal axis, it is appropriate to use a linear regression. If they are not randomly dispersed, a nonlinear model is more appropriate. So this gives us some information of the normality of our data. So we're going to start by the iris data. And you'll see what I mean by it being normally distributed. So we're going to do ggplot, lm, sepal length by sepal width, data equals iris, and geom point, aesthetic x equals dot, fitted, y equals dot resid. It should be capital for SQL. Okay, so what we had said before, in the event that the points in a residual plot are dispersed, I'll do up here. In the event that the points in a residual plot are dispersed in a random manner around the horizontal axis, so randomly along this bottom axis, it is appropriate to use a linear regression. So this is appropriate to use a linear regression. If they're not randomly dispersed, like if they're all skewed in one place, a nonlinear model is more appropriate. So let's now look at the southern states cases. So ggplot lm cases by cases 2021 data equals south cases, oops, underscore south cases, and geom point aesthetic x equals dot fitted, y equals dot resid. Okay, so now this would be a nonlinear model, right? Because see how this is kind of randomly distributed across the horizontal axis? This definitely is not. This is definitely skewed over to the left with our, we have some points kind of all over the place. So this would be a nonlinear model that you'd use. So this is important. So as a preliminary data analysis technique, if you were looking at, all right, what type of model do I want to do? Do I want to do linear? Do I want to do a nonlinear model? This is a test that you can use to determine which model, at least start to determine which model is more appropriate. We'll add a linear model. Model is not a good call for the state cases. So now let's do some correlations. So this is another thing you can do if you have some data and you want to see if two things are related to each other or at least correlated with each other. So we're going to use this data that I will provide a link to in the description of this video. Obesity insurance.csv. Okay. Okay. Let's see if I can load this now. All right. So this obesity insurance is the age, sex, the body mass index, the number of children if you're a smoker, Southwest, and the amount of the payment price of insurance for different people. So it's good data for correlations. So like I said, the link should be in the description. Or if you're doing this on Praxis, then it's in the files folder. Okay, let's look at this. So we're gonna, let's load some libraries for this. Library tidyr, library dplyr, and library plier. All right. Let's look at the structure of the data set. So str obesity. All right. So you see we have age as an integer, character for sex, number for body mass index, etc. Let's look at the column classes. So if we do class of obesity, we have, it's a data frame. And gets a summary of distribution of the variables. Summary obesity. So the summary gives us, the minimum, or the minimum, the medium, median, the mean, the max for age, the BMI distribution, etc. So it kind of gives you an idea of how your distribution of your variables are. So now let's look at the distribution for insurance charges. So we're just going to do a simple histogram, one of the built-in histograms, not the ggplot one, obesity charges. And so this is just for us to take a look, so we're not going to put any titles or anything on it. So you can see it's not a normal distribution. It's got a right tail, it's left skewed. We can also get an idea of the distribution using a box plot. So we could do box plot, which is the built-in R function. And I would use, in the previous videos you learned how to do box plots and stuff in ggplot. If you're just looking for like preliminary data analysis, sometimes it's just easy, just use the built-in functions if you're just kind of like, oh, I just want to see what it looks like. And you're not making like publication quality, you're showing it to someone else. So as you can see, we can tell this is skewed. Our outliers are the dots up here. Our mean is very close to the bottom of the box plot, so you can see the skew in this box plot as well. And we can also do box plot, obesity, BMI. So if we look at the BMI, you can see that we have a skew here, but this looks like a pretty normal distribution, right? So the mean's in the middle. We have a few outliers in terms of people that are obese way up at the top here, but not terribly off in its distribution from being normal. Okay, let's see. And actually, let's look at correlations, which we've been doing the whole time, or our aim was the whole time. The core command is used to determine correlations between two variables, or vectors, all of the columns of a data frame or two data frames. So it's the correlation between two vectors, all of the columns of a data frame or two data frames. The cov command, on the other hand, examines the covariance. The core.test command carries out a test as to the significance of the correlation. Alright, so let's start by just doing core obesity charges and obesity BMI. So is there a correlation between how much the insurance charges you and the BMI of an individual? And it's not super correlated. So 0 means absolutely no correlation, 1 means a perfect correlation. So 0.19 is kind of lower on that list. This test uses a Spearman-Rowe correlation, or you can use Kendall's tau by specifying it. So we can change and say core obesity charges, obesity BMI, and then we're going to say method equals Kendall. And that will change the statistical test to a Kendall's test as opposed to Spearman's. So we see that we have a lower correlation if we use the Kendall's test versus Spearman's. Okay, this correlation measures strength of a correlation between -1 and 1. So a negative correlation would mean it's a opposite correlation, or it is for every one goes up, the other goes down, and a positive correlation would be, for every one BMI goes up, the charge will go up. Now let's look at the Tietjen Moore test. This is used for univariate datasets. The algorithm depicts the detection of the outliers in a univariate dataset. So if we want to look and say, do we have outliers in our dataset? Is our data, you definitely want to remove or acknowledge at least the outliers when you're doing statistical tests, because they can really mess up your statistics. And so we're going to do Tietjen Moore, and we're going to make a function. So the function data series K. And then we're going to do open this bracket, and we're going to say n. I'm going to tab in n equals the length of data series r, and I'm actually going to put some. Oh, this has to be in. All right, getting ahead of myself here. Okay, and I'm going to put a comment in here. Compute the absolute residuals, and we're going to say R equals ABS for absolute data series minus the mean of data series. And then we're going to sort data according to size of residual. df equals data.frame data series R. EFS equals data frame, and then order of our data frame residuals. Create a subset of the data without the largest values. So K large equals C parenthesis n minus k plus 1 colon n. Subdata series equals DFS data series. Oops. K large. So we're going to take out the K large. Compute the sums of squares. K sub equals sub data series minus mean sub data series raised to the second power, all equals df data series minus mean df data series raised to the second power, and then compute the compute the test statistic. Sum of k sub divided by sum of all. Okay. This function that we're annotating helps to compute the absolute residuals and sorts data according to the size of the residuals. Later, we will focus on the computation of sum of squares. Okay. So, what I want to stop and say here is that it's not, if you don't understand, if you haven't taken statistics and understand sum of squares and residuals and things like that, that's okay. Understanding how to run these tests and what the output means is more important than knowing the nuts and bolts beneath it. At least in terms of my class and in my videos, there's plenty of places that you can look up what residuals and sum of squares are, or take a statistics class, which I highly recommend. Because if I dive into the statistics, then we lose the plot of the course, right? And we start getting more into statistics, which is, entire major. So, that being said, all right, we run this. We have built our function for the teach and more test. So now, let's run find outliers teach and more test function data series k alpha equals 0.5 ek is teach and more data series k. Now we're going to compute critical values based on simulation. So test equals C1 through 10,000 for I in 1 through 10,000. Data series equals R norm length data series test I equals teach gen more data series k. Capital T alpha equals quantile test alpha list T equals ek T alpha equals T alpha, and then end bracket. Okay. So what did we just write? Another long, crazy thing. All right. So this function helps us to compute the critical values based on simulation data. Now let's demonstrate these functions with sample data and the obesity data set for evaluating this algorithm. All right, so if we look at this, before we said, okay, let's look at sum of squares and our residuals and calculate our residuals for our data in this teach and more test. And then we do, okay, how do we find the outliers? Well, we say, let's take our data set and then take that number of values and then do select randomly that same number of values. So if we're using the obesity data set, we have 1,338 observations. So let's randomly check or pull from a hat 1,338 numbers, and then see how many outliers we would get by chance, right? And then compare our data set to it and see if we have ones that fall within the probability that we've created with this random permutation test. So that's essentially what we are doing. Okay, so let's annotate a little bit more and explain this. The critical region for the teach-gen more test is determined by simulation. The simulation is performed by generating a standard normal random sample of size n and computing the teach-gen or test statistic that we made above. Typically, 10,000 random samples are used. The value of the teach-gen more statistic is obtained from the data, or the statistic obtained from the data is compared to this reference distribution. The value of the test statistic is between 0 and 1. If there are no outliers in the data, the test statistic is close to 1. Oops, 1. If there are outliers, the test statistic will be closer to 0. Thus, the test is always a lower one-tailed test regardless of which test statistic is used. Okay, or we're not going to worry about this stuff because it gets too much in the statistics. All right, so first we will look at charges. All right, oops. So first we're going to do box plot, obesity charges, and then we're going to do find the outliers teach-gen more test, this one, and we're going to say obesity charges, and we're going to go to 4. Alright, so let's run this. That's not supposed to be capitalized. What? Cannot function ASB. Oh, great. So I messed up my function here. Data series. Oh, it would be down here. Oh, did I not run this? Maybe. Oh, data series minus data series. It should be ABS, absolute value of. So where did I type that? Oh, ABS. There we go. I don't know if I had to run this again, I as well. Okay, so our T is very much, we had said, if there are outliers, the test statistic will be closer to 0. So our test statistic is very, very tiny. And as you can see from this distribution, we have a lot of outliers, right? So now, let's run the same thing. Let's check out BMI, which was a lot closer to a normal distribution, if you remember. We'll do the box plot again. Box plot, obesity, BMI, find outliers, the longest name ever for a function, but that's okay. It's exactly what it does and what it says. Okay, so let's run this. K is missing. Oh, and then let's do 2 for this. So we'll check if there are outliers in the BMI, and there is, wow, it says that there are outliers, but this, what was our number up here? I thought this would be a lot lower. Interesting. Well, there are less outliers in this data, right? Because our T statistic is higher than our other one. Let me double check this real quick. And length, data series. Okay, we're gonna rerun this. I had to fix this code, so you might have to. I could not find where my typo was, so you're gonna have to look at this and see where I messed up. But this code was throwing something off, and I just had to replace it. I've been looking for a long time. Okay, so let's run this. So I want to point out this number here. This number is the suspected number of outliers. So you would have to graph your, you could expand the number of your access to kind of get an idea. I'm guessing that there's about 50 of them here. This is just an example, but if you're using your data set, you might want to do a t-test or something to look at a distribution and what lies outside of your 5% error. So if I run this, you can see that my t-statistic there's likely some outliers. This might be an underestimate of this number. There could be, because this is the obesity charges, so there's 1,300, so maybe 100 of them. If I think that there's 100 outliers, or I'm suspecting 100 outliers, you can see I have a 0.45 now t-statistic. And if I look at the body mass index, I guess that there's about 7 of them in there. I can see 1, 2, 3, 4, and then they're probably between 7 and 10. Excuse me. If I were to run this, you can see that my t-statistic is close to 1. So it says no, there's not really any outliers in there. So that is it in the for this section of data analysis. So the next thing we're going to do is we're going to get into probability plots and continue on our data analysis, preliminary data analysis journey here with video number 4. So thanks for watching. If you're watching on YouTube, hit like, hit subscribe, and I will see you in the next one.